The ancient Greeks first pondered it. What is the universe made of? They were the first to question the fundamental nature of reality, seeking to understand the building blocks of everything around them. They imagined tiny, indivisible particles called atoms, meaning uncuttable. This was a revolutionary idea, suggesting that all matter, no matter how different, was composed of the same basic units. Centuries passed, and the idea of atoms faded, then re-emerged. The concept of atoms was lost to time, buried under layers of philosophical and scientific thought, only to be revived much later. In the 19th century, John Dalton resurrected the atom. He brought back the ancient idea with a new scientific rigor, laying the groundwork for modern chemistry. He saw them as solid, indestructible spheres, like tiny billiard balls. This simple yet powerful model helped explain the behavior of matter in a way that was easy to visualize. Each element, he proposed, had its unique type of atom. This idea was crucial in understanding why different substances had different properties and how they interacted with each other. Dalton's model explained some things. It provided a framework for understanding chemical reactions and the conservation of mass. It showed why elements reacted in fixed ratios. This was a significant step forward, offering a logical explanation for the patterns observed in chemical reactions, but it couldn't explain everything. There were still many mysteries about the nature of matter that Dalton's model couldn't address. Scientists discovered mysterious rays emanating from certain elements. These rays were unlike anything they had seen before, challenging existing theories. These rays, called cathode rays, hinted at something smaller than atoms. They suggested the existence of subatomic particles, opening up a whole new realm of scientific inquiry. Then came J.J. Thomson. His experiments with cathode rays led to groundbreaking discoveries that would change our understanding of the atom forever. In 1897, he discovered the electron, a negatively charged particle much smaller than any atom. This was a monumental discovery, revealing that atoms were not indivisible after all. Thomson proposed a new model. He suggested that atoms were composed of these tiny electrons embedded in a positively charged sphere. He envisioned the atom as a plum pudding, a positively charged sphere studded with negatively charged electrons like plums in a pudding. This model was a significant step forward in atomic theory. It provided a new way to think about the structure of atoms and the nature of matter. However, the atom's inner workings remained a tantalizing mystery. Scientists continued to probe deeper, driven by the quest to fully understand the fundamental nature of matter. Thomson's plum pudding was an elegant idea. It proposed that the atom was a sphere of positive charge with negatively charged electrons embedded within it, much like plums in a pudding. This model was revolutionary for its time and provided a new way to think about atomic structure. It maintained the atom's overall neutrality, suggesting that the positive and negative charges balanced each other out perfectly. The positive sphere balanced the negative electrons, creating a stable structure. However, this model was not without its flaws. However, it raised more questions than it answered. Scientists began to wonder about the exact nature of this positive sphere and the behavior of the electrons within it. For example, how were the electrons distributed within the positive sphere? Were they scattered randomly, or did they follow some specific pattern? Were they fixed or moving? If they were moving, what paths did they follow? These questions puzzled the scientific community. Physicists yearned to peer inside the atom to understand its true nature. They needed more than just theoretical models. They needed experimental evidence. They needed a way to probe its structure, to see beyond the veil of the infinitesimally small. One tool emerged: radioactivity. This new phenomenon provided a unique opportunity to investigate the atom. Certain elements, like uranium and radium, spontaneously emitted particles. These emissions were not just random, they held the key to unlocking the atom's secrets. These particles, some carrying positive charges, became probes into the atom's heart. They could penetrate the atom and provide insights into its structure. One type of particle, called an alpha particle, held particular promise. These particles were emitted by radioactive substances and had unique properties. Alpha particles were much heavier than electrons and carried a double positive charge. This made them ideal for probing the atom's inner structure. Scientists believed they could use these particles as tiny projectiles, firing them at atoms and observing how they bounce back. This method promised to reveal the atom's hidden architecture. Such an experiment, they hoped, would unveil the atom's hidden architecture. By studying the behavior of alpha particles, they aimed to uncover the mysteries of the atomic world. Enter Ernest Rutherford, a New Zealand-born physicist who had already made groundbreaking discoveries in radioactivity. His work had earned him a reputation as one of the leading scientists of his time. Working at the University of Manchester, Rutherford designed a deceptively simple experiment. This experiment would challenge the existing atomic models and potentially revolutionize our understanding of atomic structure. He aimed a beam of alpha particles at a thin gold foil, thinner than a human hair. The choice of gold was crucial because it could be hammered into extremely thin sheets, allowing the alpha particles to pass through with minimal obstruction. Surrounding the foil, he placed a screen that flashed when hit by an alpha particle. This screen was coated with a special substance that would emit a tiny flash of light upon impact, making it possible to detect the particles' paths. This setup allowed Rutherford and his team, Hans Geiger and Ernest Marsden, to track the particles' trajectories after interacting with the gold atoms. They meticulously recorded the angles at which the particles were deflected. Based on the plum pudding model, Rutherford expected the alpha particles to pass through the gold foil with minor deflections. This model suggested that atoms were composed of a diffuse cloud of positive charge with negatively charged electrons embedded within it. After all, the positive charge in the pudding was thought to be diffuse, spread evenly throughout the atom. This would mean that the alpha particles, being much heavier, would pass through with only slight deviations. The tiny electrons wouldn't significantly impede the heavier alpha particles. Rutherford's expectations were based on the prevailing scientific theories of the time. The experiment, Rutherford believed, would simply confirm the prevailing model of the atom. However, what he discovered would turn the scientific community on its head and lead to a new understanding of atomic structure. As the experiment commenced, most alpha particles behaved as expected. They sailed through the gold foil, barely deviating from their path, but then something utterly unexpected occurred. A few alpha particles, a tiny fraction, were deflected at sharp angles, and to everyone's astonishment, some bounced directly back, as if they had hit an impenetrable wall. Rutherford, known for his colourful language, later remarked, "It was quite the most incredible event that has ever happened to me in my life. It was almost as incredible as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you." The results were baffling. How could something so massive as an alpha particle be so violently repelled by something as seemingly insubstantial as an atom? The plum pudding model could not explain these dramatic deflections. Rutherford, after months of contemplation, proposed a radical new model of the atom. He envisioned a tiny, dense, positively charged nucleus at the atom's center. This nucleus, he reasoned, contained most of the atom's mass and was responsible for the strong repulsive force deflecting the alpha particles. The electrons, in Rutherford's model, orbited the nucleus at a distance, much like planets orbiting the Sun. This vast emptiness within the atom explained why most alpha particles passed through the gold foil undeflected. Only a direct hit on the tiny nucleus would result in a significant deflection. Rutherford's nuclear model revolutionized our understanding of the atom. It provided a framework for understanding radioactivity. The spontaneous emission of particles from certain elements could now be explained as the disintegration of unstable nuclei. The atom was no longer an indivisible entity, but a complex structure with internal components. The discovery of the nucleus also had profound implications for chemistry. The chemical properties of elements, their ability to bond with other elements, depended on the arrangement of electrons orbiting the nucleus. The periodic table, a testament to the recurring patterns in chemical behavior, could now be understood in terms of the atom's internal structure. Rutherford's model, while groundbreaking, was not without its flaws. Classical physics dictated that electrons orbiting a nucleus should continuously emit energy, causing them to spiral into the nucleus, collapsing the atom. This obviously wasn't happening. Atoms were stable. The resolution to this paradox lay in the burgeoning field of quantum mechanics. Niels Bohr, a Danish physicist, expanded on Rutherford's model by incorporating quantum principles. Bohr proposed that electrons could only occupy specific energy levels or orbits around the nucleus. They could jump between these levels by absorbing or emitting specific amounts of energy, but they couldn't exist in between. Rutherford's discovery of the nucleus opened a Pandora's box of scientific and technological advancements. It paved the way for the development of nuclear energy, both for peaceful and destructive purposes. The Manhattan Project, the top-secret effort to build the atomic bomb during World War II, relied heavily on Rutherford's discoveries. But the atom's legacy extends far beyond weapons. Our understanding of the atom's structure underpins countless technologies, from medical imaging and radiation therapy to electronics and materials science. Modern computers and smartphones, with their intricate circuits and transistors, are built upon the foundation laid by Rutherford and his successors. Rutherford's experiment, a seemingly simple act of firing particles at a thin sheet of gold, shattered our perception of reality. It revealed a universe within the atom, a realm governed by laws that defied classical physics. The discovery of the nucleus marked not an end, but a beginning. It ushered in the era of quantum mechanics, a realm of probabilities and uncertainties where particles behave like waves and waves behave like particles. The atom, once thought to be the fundamental, indivisible building block of matter, proved to be a gateway to a deeper, more profound reality yet to be fully comprehended. The quest to understand the atom, initiated by the ancient Greeks, continues to this day, driving our exploration of the universe within and the universe beyond.